Imagine you are building a smart system to identify objects in images. Your system successfully spots a car, but the box around it is a little off, perhaps too wide or not perfectly aligned. How do we get that bounding box to hug the object just right, ensuring precise recognition every time? This is where bounding box regression comes into play, serving as a crucial post-processing step in object detection. It is a technique that adjusts and fine-tunes the initial predicted bounding boxes to more accurately encompass the target objects. Essentially, it takes a rough prediction and nudges its coordinates to achieve a much tighter and more precise fit. The core mechanism behind bounding box regression involves learning a set of transformation parameters that can adjust the initial box. During training, the model is fed with predicted boxes and their corresponding ground truth boxes, which are the true, perfect boundaries. It then learns a mapping from the initial box's properties, like its center coordinates, width, and height, to the necessary adjustments needed to match the ground truth. This learning process minimizes the difference between the predicted box and the ground truth, often using a smooth L1 loss function to handle outliers effectively. So instead of directly predicting the final box, it predicts the offsets or deltas from an initial proposal, making the learning task more stable and effective. In practice, this means that even if your initial object proposal network, like a region proposal network or RPN, gives a slightly imprecise box, bounding box regression has your back. After the initial proposals are generated, each one is fed into a separate regression head. This head outputs for delta values representing changes to the initial box's x-coordinate, y-coordinate, width, and height. These deltas are then applied to the original box to produce a refined, more accurate bounding box. This iterative refinement allows for significantly improved localization accuracy, which is vital for applications like autonomous driving or medical image analysis. A common technique used here is called non-maximum suppression, or NMS, which often works hand-in-hand with regression. While regression refines individual boxes, NMS helps remove redundant, overlapping boxes that refer to the same object, keeping only the most confident and best-fitting one. Together, these two steps transform a set of noisy initial predictions into a clean, highly accurate set of object detections. Understanding this interplay is key to truly grasping modern object detection pipelines. By meticulously learning to adjust bounding box parameters, bounding box regression elevates object detection from merely identifying an object to pinpointing its exact location with remarkable precision. This refinement is not just a minor tweak, it is a fundamental step that enhances the reliability and utility of computer vision systems across countless real-world applications. It ensures that when an AI system says it sees something, it truly knows where it is.